All right, so this is my attempt to teach a lecture of geometric methods in algorithm design. It was a very interesting lecture, and today this lecture was class 6 and it was taught on March 4 by Professor Khot, and it was about graph expansion, eigenvalues of the graph. It's very cute math, and sparsest cut. So we'll dive into all of these topics in detail. So first thing is, what are we like? What's the problem statement? Let's say I am given a graph with the vertices and edge set. I am told that the number of vertices are n, and I'm told that this is a d-regular graph. D-regular. What does that mean? That means that every vertex in this graph has d edges. Every vertex has d edges. That's the definition of d-regular. So what does that mean? That the number of edges then must be n vertices. Every vertex has d edges, but then I'm double counting. So number of edges has to be nd over 2, right? That is this is just the preliminary that we are working on. All right, so this is leaving a mark on the back side. So let me use another paper. Index this as 1. So let's look at this graph in terms of the adjacency matrix, right? What is an adjacency matrix? An adjacency matrix is a matrix where each row corresponds to every vertex and every column corresponds to every other vertex, and the entry is non-zero, let's say 1, when there is an edge that runs from node 1 to node 7, let's say. I am assuming all of my vertices are indexed in some manner. So there will be 1 here, there will be 1 here, there will be 1 here, and how many edges does every vertex have? It has d. So d number of these elements will be populated, all of the rest will be 0. So in this case, let's say d was 3, so 3 vertices will be populated, and every other vertex will be 0. To normalize this, what we instead would do is, let's say, make an adjacency matrix with non-zero elements are like 1 over d. That's about it. So that the sum of every row totals up to 1, basically. So d of them are non-zero, and each of them has a value 1 over d. So that totals up to 1. Something could be in a weighted, directed graph, and all of those things could be generalized. Maybe, I don't really know. That was not taught. But then let's say it's a undirected, same, every edge has the same weight kind of graph, right? So let's see what this adjacency matrix is. So this is a matrix which has some values as 1 over d and some are 0, right? Every row has precisely d elements which are 1 over d, and the rest are 0. What happens if I multiply a vector with this adjacency matrix? It's a matrix, so that it can be treated as a linear transformation. So what happens if I multiply, let's say, a vector to this? Well, if you look at it, what it does is takes the average for every node in the graph. What the multiplication with adjacency matrix does is takes the average of all of its neighbors. How? Let's have a look. So let's say x1, x2, x3, x4 were vertices, and it has, let's say, adjacency matrix which has 0, 0, 1 over d, 0, 0, something. So which column has the value 1 over d? Well, it is a neighbor. Let's say I'm looking at vertex number 1. The column which has a value 1 over d precisely corresponds to its neighbor. And when I'm multiplying this matrix with this vector, which which element is 1 over d multiplied into? Well, corresponding to precisely this neighbor. And 1 over d, there are total d such 1 over d. So what it does is, let's say this was x2. So what it does is, it does a 1 over d with x2 and it does a 1 over d with x4. Corresponding to this, it would be something like this. x1 was here, x2 was here, x4 was here, right? So what this multiplication does is takes 1 over d x2 and 1 over d x4. So what I'm saying is, let's say this vector corresponds to a value that let's say I force on this particular graph. Let's say this node has a value x1, this node has a value x2, this node has a value x4. Now if I multiply with the adjacency matrix, what I'm doing is I'm going to assign this the average of all of its neighbors, and so forth. For every node on this graph, this is the operation that happens, right? It's a very interesting thing to note that the adjacency matrix as a linear transformation takes the average of all of its neighbors. Now, what are some properties of this adjacency matrix? Let's have a look. Let's have a look at the eigenvalues. Remember, I said eigenvalues, right? So let's look at eigenvalues. Now, if you think about it, let's say, well, my claim number 1 is that the highest eigenvalue of the adjacency matrix is 1. Okay, that's a strong claim. So let's see how this happens. I have an adjacency matrix and I have a vector. What is the definition of an eigenvalue? Eigenvalue is such that a times a vector x is lambda times that x, right? Now let's look at what happens if I make my vector x as a vector of all ones. Just straight up, all ones, that's it. I assign the value 1 to every node in this graph. This is such a graph. D-regular graph, please don't mind that it's not a D-regular here. But let's say I assign the value 1 to every node on this graph. When I multiply with the adjacency matrix, what adjacency matrix is doing is taking the average of all of its neighbors. But all of its neighbors are 1, so the value at my current point will be equal to 1, right? So my lambda is 1. So first aspect of this is that there is an eigenvalue 1. Now I have to show that every eigenvalue is less than equal to 1, and only then can I claim that the highest eigenvalue is 1, right? So let's reason about why every eigenvalue must be less than 1. Now if you think about it again, let's say this is a graph and all of these vertices have some values assigned to them. Let's say 3, 4, 7, -2, 1, 0, whatever. So there must be one particular node which stands the highest. Like if you look at it in the three dimension, the node with the value 7 is the one which is highest, and every other node around it is of a value lower than 7. Now what will happen if I take the average of numbers which are lower than 7? Well, it can only bring that number down, right? So if this was 7 and I took the average of 3, 5 and 4, what is this? 3 plus 4 is 7 plus 5 is 12, divided by 3 is 4. So the one which is highest can only be brought down by taking an average of all of its neighbors. Similarly, if you look at the vertex which is the lowest, basically in this case -2, the one which is absolutely minimum, it can only go up when I take the average of all of its neighbors around it. So for let's say here it will be 3 plus 5, 8 divided by 2, 4. So it can only go up. So when I look at this value, ax equals to lambda x, some x here will be the highest x, right? And this x has to be the same here. For example, this vector was x1, x2, x3. And this one again, x1, x2, x3, and so forth. Let's say x2 was the highest value. And when I multiply it with the adjacency matrix, lambda times x2 has to be lower than x2. So lambda times x2 has to be lower than x2. Therefore, lambda has to be less than 1. So the highest eigenvalue is 1. And every eigenvalue has to be less than 1. Less than equal to 1, I mean, Every other eigenvalue has to be less than 1. Which is an interesting thing to see. So let's say I calculate, I have a graph, I have its adjacency matrix, and I can, calculated its eigenvalues, and I put them in an order. So lambda 1 greater than equal to lambda 2, greater than equal to lambda 3, greater than equal to lambda 4, boom, 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 greater than equal to lambda n. Lambda 1 has to be 1. Lambda 2 has to be some number less than 1, right? So I don't know how this is, but lambda 2, we'll see how this is. Lambda 2 represents connectedness of this graph, Lambda 2 represents connectedness of this graph. Now, lambda 2 will be equal to 1 if and only if the graph G is disconnected. Okay, that's a very interesting thing to see. Let's see how this holds. If my graph G is disconnected, that means I can put it into two separate bins, so to speak, some vertices here and some vertices here. Now, the eigenvector, let's say V1, corresponding to lambda 1 was a vector of all ones, right? Was a vector of all ones. So in this case, I want to find a vector V2 which is perpendicular to V1, but also I will assign values in such a manner such that the eigenvalue is 1. Eigenvalue lambda 2 is 1. That is, A times V2 will be equal to V2. Now here's the interesting thing. Let's say I assign all the vertices of this half as plus 1, well, of this side as plus 1, and all the vertices of this side as minus 1. Now you can intuitively see what would happen if I take the average of all the vertices here, it will remain 1, and if I take the average of all the vertices here, it will remain minus 1. So such a vector is an eigenvector to my adjacency matrix operator A, and it still remains the same value, right? Because all the vertices now are at plus 1, and all the vertices here are now at minus 1. So lambda 2 is equal to 1, and V2 is equal, AV2 is equal to V2. However, we also want to ensure that V2 is perpendicular to V1. So how can we do that? We have to, what does V2 perpendicular to V1 mean? That means the inner product of V2 with V1 has to be 0. Well, V1 was a vector of all ones. That means the sum of all elements of V2 has to be 0. So how do we ensure that? Here's the interesting bit. If I assign all of these vertices not as plus 1, but let's say as plus the number of elements in S bar, so the number of elements in the opposite side, and I assign here, instead of every vertex being the value minus 1, I assign the value minus the number of elements in that. Now let's see what happens if I take the sum of all of these. I take S times the number of elements in S bar. So it becomes S times the number of elements in S bar. I take minus S bar times the number of elements in S, So you can see both of these cancel out and it becomes 0, which means that the sum of all the individual weights of these vertices sum up to 0. So I have found a vector which is perpendicular to V1, which was a vector of all ones, and is also an eigenvector to the operator, to the adjacency matrix operator. So if my graph is disconnected, I can construct a vector in such a manner by giving the weights as the inverse, and I can prove that I have found a vector which is orthogonal or perpendicular to V1 and has the same eigenvalue lambda 2 as 1. So if my graph is disconnected, my lambda 2 is 1. Right? That was a very interesting thing to note. So this becomes slide number 5. Right? So another point that I've written in my notes here, lambda n is minus 1 if and only if the graph G is bipartite. It's another observation. Let's see how. If my graph is bipartite, that means every edge runs S bar, right? In a similar fashion, there are no edges between S, right? So if I assign every element in my S set as the value plus 1, and every vertex in my S bar set as the value minus 1, when I take the average of this, let's say, particular vertex, well, because all of its neighbors are in the set -1, its value is, after the application of the adjacency matrix operator, will turn out to be -1. And it will be same for every vertex in my set S. And similarly, for my set S bar, because every vertex has a value -1, when I take the average of +1s, which are on the other side, as all of its neighbors are on the other side, when I take the average of +1s, all of its values will become +1. So what was +1 initially has become -1, and what was -1 initially has become +1. So I have found a vector V such that the application of V makes it -V. So if my graph G is bipartite, my lambda n will be -1. Right? So that was a very nice exposition into this. Let's look at something called Courant-Fisher inequalities, which is pretty much saying that my lambda 1, which is the highest eigenvalue, is maximum AV divided by norm of V. Well, the norm of this. So what this means is lambda 1 is the maximum a vector V can be stretched by my operator A. So AV stretches it, and then divide by V is the norm of, dividing by the norm of V is like giving me a factor of how much can my vector V be stretched, right? Lambda 2 then is maximum of V orthogonal to V1, the same thing. The maximum of vector V which is perpendicular to V1 can be stretched is given by lambda 2. Lambda 3 then is the same thing, and you guessed it, it has to be perpendicular to V1 and perpendicular to V2. So AV divided by V. So this is like for symmetric matrices, we know, symmetric real matrices, we know that the eigenvectors form a basis and like they are all orthogonal to each other. So this is just like finding them. Like for example, the first one, I give you a free for all, find me the best vector, and now I fix that as my basis, and the next vector will always be perpendicular to it, and then my next vector will always be perpendicular to the span of these two, and then my next vector will be perpendicular to the span of these three, and so on. Right? This is just a way to find eigenvalues, I say, or characterize eigenvalues maybe, and we'll see more of this. Right? So the averaging, I have talked about averaging, I've talked about that bipartite, I've talked about the Courant-Fisher. Now, if you have seen my graph neural networks video, this will ring a bell. Graph Laplacian. The definition of a graph Laplacian. Well, what is a graph Laplacian? A graph Laplacian is just the identity minus the adjacency matrix. So what was adjacency matrix? It was zeros on the diagonal, 1/8 on specific elements. Now this just becomes 1 on the diagonals and -1/8 wherever there is an edge, right? This is just the Laplacian, whatever. This is the graph Laplacian. Now let's look at what are the eigenvalues of this object, this new operator, eigenvalues of L. Well, whatever were the eigenvectors of A, let's say there was a vector AV equals to lambda V. Let's multiply L, this Laplacian, with that V. It becomes identity V minus A times V, which is, well, V minus lambda V, because V was the eigenvector of A, right? So this becomes 1 minus lambda of the V. So basically every eigenvalue of my A matrix, the adjacency matrix operator, I do a 1 minus of that eigenvalue and it becomes the eigenvalue of my Laplacian operator. Eigenvectors stay the same, right? Because eigenvectors do not change. However, the eigenvalues change. So now because now I'm doing a 1 minus lambda of these, I want to arrange them in an ascending order. Initially, what was lambda 1 greater than lambda 2 greater than lambda 3 greater than lambda 4 now becomes lambda 1 prime less than equal to lambda 2 prime less than equal to lambda 3 prime, and this were the A matrices and this were the L matrix. And obviously because lambda 1 was 1 minus lambda 1 is 0. So lambda 1 prime, that is the smallest eigenvalue of my Laplacian, is 0. Lambda 2 prime is 1 minus lambda 2, right? Lambda 2 of the adjacency matrix. And this is the eigenvalue gap. So what this number means is the gap between the highest and the second highest eigenvalue of my adjacency matrix. Let me call this lambda because this is a quantity of interest. This lambda, which is the second smallest eigenvalue of my Laplacian, Laplace operator, is the eigenvalue gap of the adjacency matrix. I'm calling it the eigenvalue gap. This is a quantity of interest. This is the difference between the highest and the second highest value of my adjacency matrix, right? So this is a quantity of interest. All right, we are going to look into this, the eigenvalue gap. Let's look at what this quantity is. X transpose Lx. I'm just taking tangents here and there, but this, all of it, trust me, ties together. This is equal to, what are we saying, 1 over d sum of xi minus xj square. Let's see why. Well, this is just the sum over Lij xi xj, right? Well, Lij is 1 when xi xj are the same, so this becomes, I'm just looking at this quantity, right? I have to prove this. I'm just looking at this quantity. I should have changed the slide, I guess, but never mind. So this becomes Lij is 1 when xi xj are the same. So 1 times xi square, the sum, right? For all xi xj. Now this quantity is minus 1 over d when xi xj share an edge. So xi xj, and there is an edge between I and j, right? There is an edge between I and j. The rest, all of the elements of the Laplacian are 0. Think about it. Lij is 1 only on diagonals. Let me pull up the Laplacian definition. Because I did identity minus a, all of the L's on the diagonal are 1, and everywhere there is an edge is minus 1 over 8, right? So it allows me to split this sum over all I over all j into 2, where Lij is 1 xi square minus 1 over d xi xj. Now, what I want to do is, this is the sum over all xi's, right? I kind of want to turn it into, because I'm only looking at ij edges here, I also want to look at this in terms of the edges. So what I write here is sum of xi plus xj, well, whole square, divided by 2 when ij are edges. Minus 1 over d sum xi xj when ij are edges. Let's look at why this holds. All I've done is, I have to divide by d as well. Yeah, I forgot that. So I have to divide by d. So what I've done is, I've tried to double count them as many times as there are edges, but then because there are only d edges for every xi, I divided them with d2, right? So let's see why this happens. Let's try to systematically write it. Let's say I multiply and divide every, this is xi square for every I, for all I, right? Let's say I write 1 over d times dxi square. And I can write dxi square as xi square plus xi square plus xi square d times, right? D times. And similarly for all xj square, like xi square d times x k square d times for every particular every I, basically xj square d times. Now what I do is I club every I and j which are edges. So because xi only has d neighbors, all of these xi will find a particular, let's say this one I club with a neighbor, like, yes, so all of these xi's will find their d neighbor. So xi, maybe the first one combines with xj, this one combines with x whatever, this one combines with this neighbor, some other neighbor, this one combines with some other neighbor. And I would have double count, like I would have counted it twice, and therefore I need to divide by 2. Let's assume that that is true for now. If I let this one go for a second, I don't know how to reason about this, but I can take the 2 here. It becomes xi square plus xj square minus 2xi xj. So this becomes sum over all edges, 1 over d, xi minus xj, the whole square, right? That's what we wanted to show. Let's try to think about this. I know there is a reason behind all of this, but let's try to think. This is the sum of xi squares, right? So let me just take a vector x1 square. Let me just, x3 square. Let me just work with three element vector, right? x1 square, x2 square, x3 square. This is such a graph. Everything is, it's a d-regular one. x1, x2, x3. This is my graph. To write x1, x2, x3 square, what they are saying is you can either write x1 plus, or you can write x1 square plus x2 square plus x2 square plus x3 square plus x1 square plus x3 square. So basically every ij, and then you divide by 2, and then you divide by the degree d. So like divide by 4 essentially. Divide by 2d, or should I divide by d? I think I should just divide by d now, because then this becomes x1 square plus, so it becomes half, like 2a. Like I can see this x1 square plus x2 square plus x3 square. So I divided not by 2d, I divided by d, but then there must be a factor of 2 here because it has to sum up to this. So yeah, I mean this has to be, yeah, this is double counted. Yeah. This is double counted because Lij, where is the, yeah, it is for all I, all j, right? So when ij and ji are symmetric, so when I multiply with this L matrix, ijth element and jith element, they both contribute to the same thing. But when I reduce it to just being ij, I need to introduce a 2 here. So this part is right, and at this part has to be 2, and therefore, it turns out to this. Bottom line is x transpose Lx is 1 over d xi minus xj whole square, sum over all ij edges. Yeah, this is important because it's not a sum over all ij period. It's a sum over all ij which are edge. So that has to be taken into consideration. Now let's go to another slide, because this is where we start the interesting bit, I think. Now we're going to look into the Cheeger's result. This was so interesting because this Cheeger is Jeff Cheeger and he works in Courant. So it was very surreal to me because I was sitting in that class and learning about a theorem which has the name of a person whom I can just go upstairs and knock on the door of. Like, this is crazy. Like, if you think about it, there is this person who proved a very influential result, let's say, and he works upstairs. Like, I am studying someone's work in class and that person works right up there, like in the building. So that's crazy. So let's look at what graph expansion is. This is, I think I wrote that on my slide number 1. Look at this, look at these number of slides that I have culminated here because of my sloppy handwriting. Graph expansion. We did eigenvalues. Sparse cut we have to see. Graph expansion. That's what we are looking at now. Right? 6, 8, 9, and this is number 10. What is graph expansion? Suppose I have a graph G and it is like split into 2 sets, S and S bar. There are some vertices here, there are some vertices here, and there are edges which run from amongst and across S and S bar, right? So a graph, what expansion means, an expansion mean is, let's say if I have this set S, and if I just include the edges which are, the edges which run out of S, how much I would have expanded my graph, right? Like just taking that one step, how big is my graph now? That's like the intuitive definition of expansion. The mathematical definition of expansion of this particular set is the number of edges running from S to S bar divided by the number of edges incident on S, which is D times S. Basically, because it's a D-regular graph. There are S number of vertices and each of them have D, so D times that. There should be a factor of 2, but never mind. Let's just define it in such a manner. So a graph expansion is the number of edges running from S to S bar divided by the total number of edges incident on S. So if this number is high, that means there is a small number of edges incident on S. However, a large portion of that is actually outside S. It's actually running outside S. So that means if I take one step from S, I'm most likely going to cover a bigger set than, like, I'm going to expand my set a lot. I'm going to expand my range a lot. You can think of it also like a probability. For example, if you are in S and you are at any vertex, what is the probability that my neighbor is outside S, which is essentially this. At any vertex S, what's my probability that my neighbor lies outside S? Like my neighbor lies S in S bar, which is basically the number of edges which are outside S, like which are running across S bar divided by the total number of edges on S, right? That's like probability. So let's say, because I've written it in notes, probability that my Y is not in S when I'm given that X belongs to S and Y is a neighbor. Oopsie. But anyway, Y is a neighbor. This is given. So what's the probability that I am going out of my set? Basically, that's the kind of question. That's the kind of intuition maybe you can have of this quantity. So what is expansion of a graph? Expansion of graph. Well, H of G is the minimum over all sets. H of basically the infimum over minimum over all of these sets, all of H of S's basically. So which is the worst possible expander, and if I take any other set than that, I'm guaranteed that I have a bigger expansion than this quantity, right? I also wrote that the cardinality of this set is n over 2, and it is like, it's an okay thing to assume because whenever I split my graph into 2 sets, one of them is going to be the smaller one, so I am only going to look at the smaller ones. Smaller ones is expansion. right? So what is an expander graph? An expander graph is something which has a good expansion, let's say. So let's say an expander graph is, you know, d was a constant, let's say 20, and h of g was a constant, let's say 1 over 10. H of g is always greater than 1 over 10 something. So this is expander graph, whatever, big deal. Let's move into the Cheeger's thing now. Number 12. So Cheeger's inequality is the expansion of any graph G is less than 2 times the eigenvalue gap, it comes again, and half times the eigenvalue gap. Let me remind you what the eigenvalue gap was. If I can find that slide in this huge mess that I have created here. The eigenvalue gap is the difference between the largest and the second largest eigenvalue of the adjacency matrix, or it is the second smallest eigenvalue of the Laplacian. Same thing, because 1 minus lambda, right? So let's think about this. What this says is, if my graph expansion is a small number, that means it's a small graph expansion, that means the eigenvalue gap is low. That means that my lambda 2 is close to 1. And we have seen that because we have seen this very interesting thing. Let me try to build some intuition here. If you remember, in a disconnected graph, lambda 2 was 1. So 1 minus, basically lambda 1 minus lambda 2, this is of the adjacency matrix. Lambda 1 minus lambda 2 is 0. So for a disconnected graph, my eigenvalue gap is 0. So if we can see that for a disconnected graph, the expansion is low. Why just choose this set as my S? And because there are no edges running out of S, this number is 0. So my h of g, which is the infimum over all of these defined numbers, it is 0. So basically for a disconnected graph, this is 0, this is 0. What this means is, if my graph is, let's say, close to disconnected, this number could be, if my expansion is low, that means my eigenvalue gap is low. And that's why we also saw it when we were making a comment that this lambda 2 represent connectedness. Lambda 2 represents connectedness, right? So maybe there are some relations. Second, and I mean the idea would be the same. Let's say when we will try to prove this, with a similar, like we have the intuition now, that when my h of g is low, that means my graph expansion is low. That means there is a set which is like a very small expander. It can be shown that maybe the lambda is not that good. I mean, it's close to 1. I mean, lambda 2 is close to 1, and therefore the eigenvalue gap is really small. This side shows that if my lambda is large, that my expansion could be large, and we can if my lambda is large, that means my eigenvalue gap is large. That means my expansion can be large. This side is, I don't know, maybe let's not talk about the intuition on this side, because it's going to be a tricky one to prove that side. But anyway, let me try to get these bunch of slides in order, so we can take a break of a minute. All right. So this is the result. This is the inequality that we have to prove. Like, this is the meat of the class today, right? So let's try to prove this side. And the intuition comes from the disconnected stuff that we have, right? So if expansion is low, that means my eigenvalue gap is low. So ideal is when h of g is 0. When we found that this is disconnected, we were able to do whatever we did, right? Remember, lambda is the same as minimum. Now because we are looking at the from Courant-Fisher inequalities, now because we are looking at the second smallest eigenvalue, this is the minimum of x perpendicular to the vector of all ones, x transpose Lx over the 2 norm square. This is again I think we can show this, like, not too difficult, just assume this is true, or maybe look it up on the internet. I think this is the same as saying norm of Lx divided by x norm. I think it's the same. So anyway, so by this we have enforced that this is orthogonal to 1, because that corresponds to the first eigen value, which is 0 for the Laplacian, and this one is the second smallest eigenvalue perpendicular to 1, right? So let's say my set S is the one where the minimum expansion is achieved, right? So h of g is h of S here, which is equal to edges running from S to S bar divided by d times the number of elements in S, right? So let's consider this. Well, I made that up. Number here is S, number here is S bar, right? I want to make it perpendicular to the vector of all ones, and we have done that by assigning all of the vertices here as the value plus number of S bar, and here minus number in S, right? This is the value of every vertex here, this is the value of every vertex here. So what is the yeah, what does this vector look like? This vector basically, yeah, this is it, right? All of these vectors are S bar and all of these vectors are this. So what is the norm square of this vector? Let's look at this. Norm square is what? Norm square is xi square and the sum of xi squares, right? Yeah, sum of xi square for all i's. So let's look at this I. This I gives me the value, let's say this was I. This gives me the value S bar square. And how many of such i's are present? Well, there are total number is S. And how many here? The number given by this is norm, like number times S bar. I'm stupid. So this becomes S bar times this plus this, right? What is this? So the norm of this vector square is clear? This should be clear. Now let's look at x transpose Lx. Basically what we are doing is trying to reason about this. So we found the denominator. Now let's look at the numerator and see what we have, and we will be able to see that this is a pretty straightforward result. So this was, as we discussed, 1 over d sum of xi minus xj whole square for all ij edges, right? For all ij edges. Basically what they are trying to write here is, for all ij edges, this is the same as the number of edges running across ss prime, ss bar, and xi minus x bar is, well, s minus, you know, the because all of them are given weights which are plus here and minus here, so it becomes s plus s bar the whole square. But what about edges which are running between? For edges, yes. So what happens? Yeah, got it. So there are total ij. So for all ij edges, right? So there can be some edges which are running inside and some edges which are running outside. For edges which are running inside, xi and xj are the same because they are just not, this is this number that we assigned, right? So this contributes 0. So the only contribution here are from the edges which are running across. And for all those edges, the contribution is the same because of the way we assigned values. So this becomes 1 over d edges s, s and n square. So we found the numerator, we had the denominator, right? We did find the denominator. So let's just do it then. X transpose Lx divided by norm of x square is 1 over d edges s, s bar n square divided by this is s, s bar n, right? I cancel one here. Yeah, I cancel one n, and there is a very nice argument now. This is 1 over d edges s, s bar, 1 over d times the number of edges in s times n over s bar. Now this is the h of g, and this quantity is always less than yes, this quantity is always less than 2. Why? Because s bar was basically we split it into 2, right? S and s bar, and s bar is of size greater than n over 2. So n over s is always less than, n over the number of s bar is always less than 2. So this is always less than h of g times 2, and this and on the left hand side we have is the x transpose Lx over basically the eigenvalue gap. So this is always less than x transpose Lx over x, and this quantity is always greater than the eigenvalue gap because eigenvalue gap is over the minimum of all such numbers, right? So what I have is that my lambda, which is the eigenvalue gap, is less than h of g times 2. This was the first side. How is it the first side? Well, h of g is greater than lambda half. Take it down. Like take this 2 here, and this side is proven. Let's go over the proof again because I think I was not very clear on this one. Basically, we want to find the minimum over x transpose Lx over norm of x square. I went the same direction as when we were talking about disconnected graphs. We did the same thing, assign vectors in the inverse size manner, and we look at x transpose Lx. X transpose Lx is norm xi minus xj. Xi minus xj square, sum over all ij edges. When I, j are in the same set s or s bar, these two cancel out. The only terms which contribute any values are ones which are running across, and therefore this quantity. And x transpose Lx divided by norm x square is this. Take the s bar is a bigger of the set, so this thing is always less than 2, and therefore it is always less than h of g over h of g times 2. And this is always greater than lambda because lambda is the minimum of all x's which are perpendicular to the all ones of this quantity, norm x square, and therefore lambda is less than hg over 2. Great. I understand it now. All right. Now let's look at the other side. h of g is less than 2 lambda. To talk about intuition, when graph was disconnected, lambda is 0 and therefore expansion is 0. So if you want to say that, here we said that if my expansion is small, my lambda would be small. Now here I want to say if my lambda is small, the expansion is small. And maybe we can, build some intuition from there. So we hope that if we think of lambda as small, from there maybe we can conclude that my expansion is small. Expansion is small, right? So let's say my V2 was the eigenvector of this Laplacian, second smallest eigenvector. So that means that my V2 is perpendicular to V1 and it satisfies this equation that I have written here. LV2 is lambda times V2 and V2 is perpendicular to V1, right? Let's say I run it through a computer and I have found the value of V2 and it has some values like beta 1, beta 2, beta 3, boom, 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 boom. And because this has to be perpendicular to the vector of all ones, there will be some positives and there will be some negatives, because all of these have to sum up to 0. So some of them will be positive, some of them will be negative, right? Some of them will be positive, some of them will be negative, let's say. Now, what I want to do is, let's say I can, after I calculated this, by the magic of knowing things in hindsight, let's say I arranged my vectors, I arranged my graph vertices in such a manner that my V2 was a descending vector. So beta 1, beta 2, beta 3, up to beta n, they were all like descending. And I can do that because let's say first of all, I had the graph, I numbered all of these vertices arbitrarily, right? And I found this particular vector. Now what I do is take the highest value of this, make that the vertex 1, and then that the vertex 2, and then the vertex 3, and then the vertex 4, so that my V2 is now in complete descending order. So what happens now is something interesting. There is some number, beta 1, beta 2, beta k plus 1, beta n, right? There is a number from where this entire vector goes from being positive to being negative. Let's say this was this line 0. So this beta k is such a number where this is the smallest positive number on this entire vector V2, right? Let's say I define my beta to be beta 1, beta 2, beta k, and the rest are all zeros. I just define it like that. This is obviously not perpendicular to V1, but let's say I just define it, and we will use this beta to give reasons about this. Why are we doing this? Why are we doing this? Why are we trying to do this? So the intuition behind all of this was, if I can show that my lambda is small, that means maybe the graph expansion is small, right? Now how is lambda, what was lambda? Lambda was this big number, big this quantity, whatever, right? What we want to show is that if I can find some subsets of the graph, let's say A1, A2, A3, A4, boom, 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 and I want to show that one of these sets has a low expansion and then maybe related to the lambda value, right? Some of them, or one of them, has a low Hg. Now instead of showing just one, maybe what I want to show is if I take some sort of an average of the expansion of all of these sets, an average quantity, if that is low, then my lambda is also low, because if one of these is low and if I'm able to relate it to lambda, if an average is low, that means one of them was lower than the average, one of them was higher than the average. But then if one of them was lower than the average, I have basically concluded it, right? Or maybe what I want to show is just not a simple average, but some sort of a weighted average. If that is low, then it doesn't matter what weight I choose, this lambda would be low again. So these are some quantities, like this is some sort of rationale that I'm trying to give, but you know, we'll see. It's not that easy. This was tricky even for me to understand on the first go. So this was not easy. I constructed this vector beta by some magic, beta 1, beta 2, beta k, where all of them are positive and the rest are zeros up to, let's say, nth and n elements. What I take is now my candidate sets, like I said, let's say L1 is just the first one. L2 is 1, 2. Basically, I slice it here. L3 is 1, 2, 3. L4 is 1, 2, 3, 4. I construct k such candidates. Now what I want to show, if I can conclude about the expansion of each of these sets, and I can say that the expansion is low. If my h of g is low, that means my lambda is also, I mean, if I am able to conclude it in that manner, then I'll be golden, because if for each of these sets, or for the average, or for some weighted average, and the h of g of weighted average of this, if it's related to lambda, I'm golden. If it is related to lambda, and if I can show that this side is low, this side will be also low, and you know, I'll be able to get to that inequality. Tricky stuff. So maybe show that one of these sets has a low expansion, like less than 2 lambda, maybe less than square root 2 lambda. I don't know where this came from. Oh, well, I know, hindsight, but maybe show that one of these sets has an expansion of less than square root 2 lambda, or an average has an expansion of less than square root 2 lambda, or a weighted average has an expansion of less than square root 2 lambda. So let's see. Let's just bear with me. Now what Cheeger showed is this. Now if you were trying to prove this quantity, how would you proceed? You would obviously, because you have this beta vector constructed, and you know x transpose Lx follows this kind of regiment. You know that xi minus xj the whole square divided by 1 over d, that is the format, that is like the form of x transpose Lx, right? Maybe you would try to do something with this vector, maybe, but it turns out that you cannot. You really need to reason this quantity for some reason, and yeah, it works. It just works, basically. That was the discussion in the class as well. Professor said that every time I teach, I try to prove that if I can use this quantity, because this is the most natural thing you would use, because you have been doing this the entire class when you made x transpose Lx to be equal to this quantity, you know, where I lost my train of thought for a bit, and we painstakingly derived this. That x transpose Lx is 1 over this. So maybe when I plug my beta vector here, it should be beta I minus beta j whole square. Maybe that would be the case, but it turns out this quantity is the one which just works. So what's the goal now? That given this intermediate quantity, this is less than square root lambda up to some constant, let's say, and it is greater than h of g, right? Some constants, whatever. Now why this quantity is like helpful, let's say. This quantity is helpful because it's like a telescoping sum. Let's say I look at all ij edges, beta I minus beta j whole square. So if my vector beta was something like this, and there was an edge running from 1 to k, so I will have a beta 1 minus beta k whole square, right? What I can write it as is beta I square minus beta I plus 1 square plus beta I plus 1 square minus beta I plus 2 square plus beta I plus 2 square minus beta I plus 3 square, right? Now, why is this quantity, why did we write it like this? Because now if we try to sum up just the particular, beta I minus beta I plus 1, let's just look at this particular one. So let me write my beta vector first to make it easy. It's beta 1, beta 2, beta I plus 1, beta k, and zeros. How many times am I going to encounter beta I square minus beta I plus 1 square? I'm going to encounter beta I square minus beta I plus 1 square whenever there is an edge which crosses this boundary. Whenever there is an edge which runs from here to here, let's say from the left hand side of this particular boundary to the right hand side of this particular boundary, whenever there is an edge of such fashion, I'm going to run into beta I minus beta I minus beta I minus beta I plus 1 square. Why? Because when I try to break this edge into the telescoping sums of all of these intermediate betas, I'm going to run into beta I and beta I plus 1. So what I'm claiming is this quantity 1 over d beta I square minus beta j square sum over all I j edges is the same as going from I to 1 to n minus 1. The number of edges crossing Li and Li bar beta I minus beta I plus 1 whole square. Right? Now you see the point. Now is it ringing any bells? I created my level sets in such manner, in just this manner, where I put a boundary here, then I put a boundary here, then I put a boundary here, then I put a boundary here. And now this quantity is the same as the number of edges crossing this Li bar times this number. And this Li bar, if I divided by the number of elements in Li, maybe is somewhat related to the expansion thing that we were talking about, right? But here's the kicker, like this is the kicker, number one, big one to understand. And this is easy, like if you arrange all of these betas in a line, and this one is Li, this one is Li bar, that means this one was beta I and this one was beta I plus 1. Every time an edge crosses, I was coming with a telescoping series, like beta 1 minus beta 2, beta 2 minus beta 3, 3, 3, 3, 3, 3. I would have run into beta I minus beta I plus 1, no doubt about that. If my edge was just on the left hand side, I would have, when I was writing the telescoping series, boom, 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 I never ran into beta I or beta I plus 1 for that matter, right? So the number of times this quantity beta I minus beta I plus 1 was encountered in such a telescoping series for all ij edges was precisely the number of edges crossing such a boundary, right? And now I wrote this for all n's, and we painstakingly wrote that vector in such a manner that beta I right after some k is all zeros. So this is going to be greater than or equal to sum from 1 to k beta I minus beta I plus 1 squares and edge Li bar, right? Because I just let's just truncate this sum. Let's just truncate this sum after k elements. So this is always going to be greater than this particular sum. Now because h of g is the smallest of all of these, smallest expansion, what I can write is that this is always greater than equal to beta I minus beta I plus 1 square, squares everywhere, I going from 1 to k, divided by t times, d times the number of Li. So this is basically what I was trying to say is Li d h of g, right? Beta I minus beta I minus beta I this quantity times if I multiply it divided by Li, this becomes the expansion of this particular Li, and that is always greater than the minimum such expansion. And this is trivial, like this is easy to see. Now, Li though is always equal to I, because that's how I chose my Li. Li was 1, 2, 1, 2, 3, so L4 was number of elements. Number of elements in Li is always I. So this sum is a telescoping sum, beta I square minus beta I plus 1 square times I times d times h of g, which I can just pull out, right? Now this telescoping sum is a very cute little thing. If you think about it, this becomes beta 1 minus beta 2 square plus 2 beta 2 square minus 2 beta 3 square plus 3 beta 3 square minus 3 beta 4 square. So these terms result out in a in a nice fashion. This telescoping sum turns out to be just d times hg times just the norm of beta square, 2 norm, because it just becomes beta 1 square plus beta 2 square plus beta 3 square plus beta 4 square. Like because of this telescoping sum, all of this is, you know, it turns out to be. So wait, first thing, let me track back all the way. We started with beta I minus beta j square, I, j are edges. And now we have shown that this quantity is greater than d times hg times the norm of beta square, 2 norm. And all of this beta is again the zeroed out, the truncated zeroed out thing, right? We wanted to start from this particular intermediate quantity, and it just works from here. So beta I minus beta j squares is always greater than or equal to this. We proved it in the first. This is number 1. Now number 2, which would have been number 1 if we were doing this ourselves. Beta I square minus beta j square is sum beta I plus beta j times beta I minus beta j, right? For all edges ij. This lends to the application of Cauchy-Schwarz. For now, if I look at this as every sum as ij, what this is inner product of these two is always less than square root of this, like the norm of this. So beta I plus beta j whole square sum times square root of sum beta I minus beta j whole square. Now beta I minus beta j whole square is actually beta transpose L beta. I mean, you know, because this is of the same format, right? If I divide it by d, it becomes beta transpose L beta. So I multiply it by d to ensure this stays the same. This quantity is converted to here. What about this? What about this? This uses the fact that 26, slide 26. Sum of beta I plus beta j whole square. So this uses the fact that a plus b whole square is always less than 2a square plus 2b square. Yes, and it can be seen a square plus b square plus 2ab is less than 2a square plus 2b square. That means a minus b whole square is always greater than 0. So this is right. So this is always, so for all summing over all edges, taking the 2 as the constant, beta I square plus beta j square, and this is d times the norm of beta square with the square root. So we started from here. 1/2 is calculated by using Cauchy-Schwarz, by using Cauchy-Schwarz. We went to this, and here we have found that this is less than equal to 2d norm beta square root, and also beta transpose L beta d square root from the beta I minus beta j thing, right? So what I can do is now take the d outside, take the multiply divide by norm beta. So this becomes basically what I'm trying to do is multiply divide by norm beta now square here, and multiply, like take it outside. So this becomes norm beta square d 2 times beta transpose L beta divided by norm beta square root of this. Now what I have now let's look at this for a second. What I have proven is combining these two, this intermediate quantity, I'm gonna just label it like this. It is less than equal to 2 times norm beta square, or d times, and 2 times this number in the square root, and it is greater than d times h of g norm beta square. So d and d can cancel, norm beta and norm beta can cancel, and this probably, after some reasoning, oops, I don't know if you can see, the intermediate quantity was less than d times whatever by the, and how did we prove the right hand side? Doing a plus b, a minus b, a plus b Cauchy-Schwarz, a minus b whole square, basically Cauchy-Schwarz, and then a sum, and then the b transpose L beta, and it's always greater than this. And how did we prove this? We proved this using the this was simple, by taking the telescoping sum basically over all L sets, right? So now I see hg here, and I see this quantity, and maybe this quantity reminds me of the definition of the eigenvalue. So maybe if I can claim that, if I can somehow claim that beta transpose L beta divided by norm beta square is less than my eigenvalue, if I can claim that, then I'm done. This thing is done, right? So let's see. My beta vector was beta 1, beta 2 up to beta k, and then all zeros. What is beta transpose L beta? It is the sum of beta i's with L beta I. So like I apply L to my beta vector, take the ith and multiply it with beta I. Now, because my beta I is 0 after k, I only need to look at the first k elements of, L beta, because the rest of all are multiplied with 0. So let's see what L beta is just for the first k elements. It is, let's say for the ith element, it is me myself minus 1 over d times all the neighbors that I have, all the neighbors and the average of those betas, right? Now if I'm looking at the first k elements, beta I is same as v of I, which was the vector, like the actual eigenvector, which has the lambda eigenvalue, minus 1 over d sum of my neighbors, which are in the beta fashion, like in the beta zeroed out fashion. Now if some of them were 0, this number could have only gotten higher. Yes. Understood. One second. Let me recalibrate. This is my beta vector. And what I claim is that when I multiply with L and take the ith, just look at the ith component, and I is less than k here because we only need to look at the first k ones. This is beta I minus 1 over d ij, like ij is an edge, beta j, right? Now because I'm applying my L to my beta and I'm taking only the first k elements, my beta I is same, because I'm only applying it to the first I ones, my first k positive ones, beta I is same as wi, right? And beta j is something like this. If this was my w vector, right, it was, sorry, v vector, which was going from positive to negatives, betas are positives and then capped at 0, like here. So what I'm saying is my betas are always greater than or equal to my w's. So my minus betas are always less than equal to minus w's. So this number is always less than equal to minus 1 over d wj, because wj could be a negative number, and negative of that negative number makes it a bigger number than this is, and this is less than equal to, well, this is just L times w ith, and L times w ith is the same as lambda times w ith, right? Because this is the eigenvector. And well, so L times w ith is equals to lambda times w ith, which is the same as lambda times b ith, because we are only looking at the first k elements, and in those cases wi is same as w beta I. The main one was this one, that beta is always, the beta vector is always greater than my w, because w can be negative, beta is always positive. So when I multiply with the w's, some of these numbers could be negative, and they could make this number bigger because of the negative of the negative being, like, making it a higher quantity. So what I'm saying is now L beta, the ith one, is less than lambda beta I. Summing over just the first k elements, beta I, lambda beta I, is less than lambda beta I, only the first k, and which is essentially lambda norm beta square, because it only has the first k elements, the rest are 0. So my eigenvalue lambda, eigenvalue gap, the one which is corresponding to the best eigenvector, well, which is corresponding to the eigenvector which minimizes it, is always greater than beta transpose L beta divided by norm beta square, right? So now, bringing all of it back into this new slide, the intermediate quantity that we defined is less than d norm beta square 2 times the eigenvalue gap, and this is always greater than h of g. So h of g is less than 2 lambda eigenvalue gap. Let us let me collect these slides again, and let us go over all of it once again, the Cheeger's proof specifically, because it was nice and complicated, and I like things which are complicated. Where is number 13? There is number 13, 14, 15, 16, 17, 18, 19. It was a good thing to number them, because if I did not number them, which I didn't in the last couple slides, oh, it's gonna be a messy one too. So I have 22, I do not remember where 23 is. And oh, there it is, 23, thank God. 24, 25, 26, and after 26, I did not label them. And therefore, we have to do this again, assuming this comes here. This was 27. So where do you think I went from here? I went to try to prove this one, right? So I went this, and this. Got it. Awesome. Great. 27, 28, 29, 30, 31. I used 31 sheets of paper in 1.5 hours to make this lecture. I don't want to go through graph expansion, everything. I just want to go through the Cheeger's result again, because that I think is the one which is more important. I hope, is it visible? Oh, is it not? Crazy. Man, it would be really, really upsetting if at the end when I look at the video, I'm gonna find that half of it was off the recording window and I would have missed so much of it. It's gonna be really upsetting. We wanted to prove that this Cheeger's h of g, which is the expansion, is less than 2 lambda, which we did in a very painstaking, I am losing my mind way, and it is greater than lambda. The greater than part, how did we do it? Let's try to remember. Let's try to see if we can do it ourselves. We recall that lambda is this quantity. This quantity is just xi minus xj whole square. And xi minus xj, we constructed those two sets, which were reminiscent of the disconnected proof, and we applied xi minus xj on that. The only thing was that xi minus xj, when they are on the same side, they contribute nothing. When they're on the other side, they contribute something, and that contribution is this. And then we divided by the norm. We calculated the norm by definition, and it lends to very cleanly that h of g is greater than lambda over 2. Great. H of g less than 2 lambda. What we did was assume that there was this vector which gives this lambda eigenvalue, arranged all of these vertices in a descending manner like this, and floored it at 0 such that beta can only be above 0, all zeroed out when they are negative. Now what we did was use this beta and an intermediate beta quantity beta I square minus beta j square to reason about a weighted average of sets, of all of these sets. And what was that weighted average? The weighted average was precisely beta I minus 1 square. Like this was the weight and this was the expansion of that set. So this is how we proceeded. We arranged them in a descending order. We took level sets. We took level sets up to k of increasing size increasing by 1, and we wanted to show if the expansion of a weighted average of these sets, if at all can be related to the eigenvalue gap lambda, right? And if it is related and if it is small, then we can conclude that. If let's see if there is an inequality that exists. So we use beta I minus beta j square. This is an intermediate quantity. Now we have to construct some inequalities on the left hand side, on the right hand side. We want to show that h of g is less than something. So we want to show that h of g is less than this, and this is less than square root lambda. So to show that h of g is less than this, what we did was write the level sets and take a sum and see that all the edges which are telescopingly summing up, they are only appearing when they cross some sort of a boundary. So we wrote this in a telescoping manner, and we saw that they only contribute when there is some boundary, when an edge crosses this boundary. And what is this boundary? This is precisely Li bar when my edges are running from Li to outside Li. So this is the same as running from I to n minus 1. Edge is running from Li to Li bar, beta I minus 1 square. This is not the whole square, this quantity, right? Yeah. Now edges of L, this can be lower, like we can truncate it to K, wouldn't make a difference. And this is always higher than the minimum graph expansion thing. And graph expansion thing, and we can just put LID. And interesting to see that Li is of the size I. And I take telescoping sum, and this just reduces to the norm beta I square. So h of g is always less. H of g times something is always less. So I found one side relation of h of g. Now to look at the other side relation, beta I square minus beta j square is beta I plus beta j times beta I minus beta j, like a plus b, a minus b. Cauchy-Schwarzing it becomes a plus b square, a minus b whole square, multiplication of these. Now this was the same quantity as beta transpose L beta, because that's how L works. And this was always less than the 2 times d times the norm of beta square. To show that beta transpose L beta was less, now the claim is that this quantity is less than the smallest eigenvalue. And how did we do that? We did that by looking at the vector beta, seeing that it's capped at 0. So beta transpose L beta, we only need to look at the first k ones because the rest of them are 0. And the first k ones was, well, beta I minus something something, and beta I is precisely Vi, and this, the negative of this can only be less than the negative of my weight vector V, because if my weight vector goes to negative, my beta is capped at 0. So minus of beta can only be, like, it can go up till 0, where this could give a positive value. So this is always less than this vector, which is essentially just LVI and LWIth element. And because it's an eigenvector, it's lambda times the WIth element. And where WIth element is same as beta I, because we are only looking at the first k ones. So we proved that this is L beta ith is less than lambda beta ith, and therefore this sum, which is beta transpose L beta, is less than lambda beta square, and therefore lambda is greater than beta transpose L beta. So we had that intermediate quantity. That intermediate quantity was less than this square root 2 lambda, which is just the newly derived result, and it was greater than hg something, which we found using the telescoping aspect of my this was the intermediate quantity. It is greater than this d beta square, and d beta square was present on both sides, so they cancel, and h of g is less than this particular number. And this is pretty interesting, you know, the way the level sets were defined, something the professor said at the end, which was very hand wavy, but it was awesome to me, because what is a graph? You know, what is a vector? What is this? What is this thing, huh? It's a graph, some values. And what is a vector? A vector is something that assigns a number to a particular node. And what we are doing is, let's say if this graph was arranged in a 2D plane here, this graph, what we are doing is looking at the value assigned to every, you know, vertex, and taking the one which are highest. The first highest, the second highest, the three top values. But why restrict to graphs? Why not this be a continuous thing defined on let's say a real value? So what is a vector? A vector is something that just looks at that point and gives a value to that. Well, that's a function essentially. That's a discretized way of saying that this is a function. So if I have an operator working in this 2D dimension, and when we look at its particular eigenvector, that eigenvector is nothing but a function. which gives a value to every element on this graph essentially. What I'm saying is, instead of looking at discrete nodes, I look at every particular point as a vertex in a real plane, you know. So then that eigenvector is not just a vector, it's a function, and that's just so crazy to me, because a vector is just a special case of a function. So every linear operator, the Hamiltonian, you know, in quantum mechanics, this is just an operator, and we find an eigenfunction and it gives an eigenvalues and times that function. Like, this is crazy, because what is a function? A function just takes in a value and assigns it another value. Well, that's just a vector. A vector is a function, and this is just amazing to me. So what we did was just take level sets. So if we were in, let's say, continuous geometry, this was, let's say, the eigenfunction, we could be taking level sets of such a manner, and this is just mind-blowing. This was crazy to me. The fact that vectors and functions and all of these are just interchangeable, and they are just generalizations or special cases of each other. It was just mind-blowing stuff. So yeah, that was the big lecture, and this was a very interesting one because I don't want to forget this, and the only reason I make this video is because I want to remember and maybe come back and look at it. Like, geometric methods in algorithm design, class 6. Graph expansion, eigenvalues, sparsest cut, next video.